In today's lecture, we're going to be looking at paths between points in a graph, between vertices in a graph. And our goal is to try to find the shortest route between any two vertices. So this is a very natural question, and it comes up in some pretty familiar settings. So, for example, I don't know whether you've ever wondered how your Satnav works. So when you get in the car and you program your Satnav to find the shortest route between, say, Oxford and, I don't know, Cambridge, then how does it do it? Well, obviously it has stored in its memory a graph which represents the road network of the UK. And each edge of the graph has a length associated to it, which maybe is the amount of time that you can travel along that road, how long it takes to travel along that road. And so what the Satnav does not do is it does not go through every possible route from Oxford to Cambridge. There are just far too many of them for it to be able to do that. Instead, it turns out that there is an efficient algorithm for finding the shortest route between two vertices. And that's what I'm going to be describing today. So the setup is very natural, I think. You start off with G, a connected graph, say this one here. And each edge has been assigned a positive length, L of E. And so once you've assigned lengths to edges, it makes sense to talk about the length of paths. So the L length of a path P is just the sum of the lengths of its edges. So we use the terminology L length rather than length because we've already defined what we mean by the length of a path. It's just the number of edges in that path. But we obviously want to have a notion which takes account of this function L, which assigns to each edge a positive real number. So that's why we talk about L length. But because L length is a bit of a mouthful, in today's lecture, whenever I say length, I mean L length. Okay, so what we're interested in is L shortest paths between two vertices x and y. So an L shortest xy path is, by definition, an xy path that minimizes the length. And it's not at all obvious how to find that. So, for example, in this example of these two vertices x and y, the most efficient route to get from one to the other is not to go along this edge here, because that has length 4. In fact, the most efficient route is to take this red path here, because that has length 3. So Dijkstra's algorithm is what we're going to be describing today. And what it does is for any two vertices x and y, it finds an L shortest xy path. So the idea is that we think of x as fixed in some sense, and we're going to think about all possible vertices y. And what the algorithm does is it maintains a tentative distance from x, called d of v, for each vertex v of the graph. So d of e is going to change as the algorithm progresses. D of any vertex v can be a non-negative real number, or it can actually be infinity as well. So this function d from the vertex set to the reals together with infinity, it's important to realize that this is going to change as the algorithm progresses. But at each step of the algorithm, we finalize d of u for some vertex u. After that, it won't change. By the end of the algorithm, we finalize d of u for all of the vertices u, and it'll be equal to the correct value. Namely, d of u will be L of p star of u, where p star of u is some L shortest xu path. Okay, so that's the way that the algorithm is going to work. So what the algorithm does is it keeps track of a subset u of the vertex set. So initially u is the entire vertex set. So u is the set of vertices for which dv has not yet been finalized. So in other words, you should think of as the set of uncertain vertices, ones that we're not yet sure of for what the final d value of that vertex should be. So initially, u is the entire vertex set. So we're not sure of the d value of any vertex in our graph. The algorithm starts with the d value of the base vertex to be 0 and d value of every other vertex to be infinite. Then what does it do? It keeps on repeating the following step. If u is empty, we stop. That means that there are no vertices with uncertain d value. We've finalized the d value of all vertices, in other words, and so we could stop. Otherwise, we pick some vertex u in u for which du is minimal. Then what we do is we delete u from u. And in other words, we finalize the d value of u. And we also do the following. For any vertex v in u, with v adjacent to u, and satisfying this inequality, namely that d of v is strictly greater than d of u plus the length of the uv edge. If that's the case, we replace d of v by d of u plus L of uv. So in other words, that has reduced the d value of that vertex v. Okay, so it might not be obvious what the algorithm is doing. It's really best to look at an example to start to get a feel for how this algorithm works. So here's an example. Here's our example. Here is our graph with the lengths assigned to its edges, and here's our vertex x. And I've coloured all of the vertices red because they're in our set U of vertices for which the d value is not yet certain. So initially, we set d of x to be 0 and d of all of these other vertices to be infinite. Okay, so the first stage is to pick the vertex with smallest d value. That's x in this case. In fact, it's always x. And we remove it from u. In other words, we finalize its d value. And what we do is for every vertex v adjacent to u and satisfying d of v is greater than d of u plus luv, we replace d of v by d of u plus luv. So in other words, we should go through each of these vertices that are adjacent to this vertex x. And we ask ourselves, is its current d value greater than the d value of x plus the length of that edge, joining x to that vertex? Well, in this case, the answer is definitely yes, because this is infinite here, and d of x plus 1 is definitely strictly less than infinity. So we should replace that vertex, the d value of that vertex, by 1. And similarly, we should replace the d value of this vertex by 3, this one by 4, and this one by 1. Okay, so we've done the first step of the algorithm. Let's continue. Now we have to pick a vertex in U, in other words, one of these red vertices, with minimal d value. There are two of them. There's this one down the bottom and there's this one on the top. Let's pick the one on the bottom. So we finalize its d value. That means we remove it from the set U, so that vertex is no longer red. And then we look at all of its neighbours that are in U. In this case, there's just the one of them, this vertex here. And we ask ourselves, is the d value of that vertex V strictly greater than the d value of U plus the length of the edge UV? Yes, it is, because 3 is greater than 1 plus 1. So we should replace this 3 by a 2. Now we continue. Again, we look at the vertex with smallest d value is this one on the top. So we finalize that. And then we look at all of its neighbors and we ask ourselves, is the d value of, well, in this case, all of its neighbors in U, this is just one of them, is that d value strictly greater than the d value of U plus the length of that edge? Well, in this case, 4 is less than 1 plus 5, so we don't change that. Okay, so now we look at the next one here. This is the next vertex that we this is the next vertex in U with smallest d value. We finalize that one. We look at all of its neighbors in U, that's just this one, and we say, should we be decreasing their d value? Well, in this case, we should, because 4 is greater than 2 plus 1, so we should reduce that to 3. Now we come to the final step of the algorithm. This is the last vertex, and we finalize its d value, and we stop. And as you can see, the d values on these vertices really are correct. They do represent the length of the shortest path, the L length of the shortest path from X to that vertex. So for example, we saw that the shortest path from X to this vertex here was going around these edges with length 1, and so that the correct d value there is indeed 3. Okay, so it's done the correct job. In fact, Dijkstra's algorithm can be used to do more. What it can do is it can be used for any vertex X to construct a spanning tree T with the following property: that for any vertex Y in the graph, the unique XY path in T is actually an L shortest XY path. So it's quite surprising, in my view, that such a tree should exist. We call such a tree T an L shortest paths tree rooted at X. So let me give you an example. I've highlighted here in red such a shortest paths tree. And you can easily check that the shortest way of getting from any vertex to x is to go via the edges in this tree. So that is what a shortest paths tree, that's its defining property, that the shortest way of getting from any vertex to x is to follow the unique path in the tree from that vertex to x. Okay, so how can we, what does Dijkstra's algorithm do? How does it create this tree? Okay, so we're going to describe how to obtain the tree T. Okay, so here's our example that we're looking at. So what it does is for each vertex v other than the base vertex x, we define its parent. So the parent of our vertex v is the last vertex u with the property that we replaced d of v by d of u plus luv during the algorithm. So if you remember, for every vertex, we kept this tentative notion of distance d from x. And this d, as the algorithm progressed, kept on going down. And at some point, it stops. Now, when it goes down, the way that it goes down is that d of v goes down to the value d of u plus luv for some vertex u. And so when it goes down for the last time, that u is called the parent of v. So, for example, in this case here, when we ran the algorithm, we first of all finalized x, and then we finalized v, this vertex v here, and before we finalized it, we reduced the d value of v by saying that it was the d value of x plus the length of this edge. So in other words, x is the parent of v. Okay, so I've drawn in red the parent of v. The next stage of the algorithm was to finalize this vertex here, and its d value had gone down from infinity to 1, and when it went down from infinity to 1, that was because it was equal to the d value of x plus the length of that edge. So the parent of this vertex here is also x. The parent of this vertex here is this vertex v, and so on. And so what we do is we create our tree. So we obtain our tree T by drawing an edge from each vertex v other than x to its parent. Okay, so this is the algorithm, and it's not at all clear that it does the right job. And in fact, I'm going to be spending the rest of the lecture explaining why the algorithm does work. So I'm going to start by proving a lemma, which is going to give us some structural results about T and about D. So it has two parts to it. The first part of the lemma is that T is indeed a tree. It's clearly therefore a spanning tree, because if you remember, the way it was defined was for every vertex other than x, there was an edge going from that vertex to its parent. So in other words, this really does cover every single vertex of the graph. So once we've proved this lemma that proves that it's a tree, we'll have that T is a spanning tree. But we won't yet prove that it's a shortest paths spanning tree. Instead, what we'll do is prove the following. That for each vertex u, d of u we'll show is equal to the length of P of U, where P of U is the unique XU path in T. So that'll be clearly a useful thing to do. So the final thing that we claim is that the shortest way of getting from U to X is by following this path, this unique path, PU. So we haven't proved that, and this lemma isn't claiming that yet. But what it's claiming is that D of U is the length of that path PU in T. Okay, so let's prove this lemma. So at each step, we have our subset U. And we're going to let C be the complement of U. So C is the set of vertices for which the D value is certain. That's why it's called C. It's been finalized. Those are the vertices for which it's finalized. And it's certainly the case for every finalized vertex with finalized D value, we know what its parent is, because we know the last time that we decrease that D value, and hence we know what the parent of that vertex is. So we can certainly have defined the parents of all the vertices in C. Okay, so let me just run through this algorithm again in this particular case, keeping track of the red vertices, which are the ones for which we're not yet certain. So as we run through the algorithm, you can see that the black vertices, the complement of U, is growing. So those are the vertices in C. So let T of C be obtained by drawing an edge from each vertex in C minus X to its parent. So V of TC is C. So here's an example. For example, we're halfway through the algorithm here. What we've done is we've finalized the D value of X, and we finalized the D value of this vertex here. So C consists of these two vertices, and U is the remaining vertices. And so because we finalized the D value of this bottom vertex, we know what its parent is. We know that it's X. And so we defined TC, which is the graph which is obtained by going through every single vertex in C other than the base vertex and adding in the edge which goes from that vertex to its parent. So V of TC is C. So the next stage, for example, we've enlarged C and thereby enlarged T of C. And so on and so forth. So you can see that what we're doing is we're gradually building T. We're just adding in the edges of T one by one. And at any given stage, we've got this graph TC. So what we're going to do is we're going to show by induction on the cardinality of C that TC is a tree. And for each vertex U of TC, in other words, each U in C, we have that D of U is L of P of U. In other words, the length of the unique XU path in TC. So that'll clearly do the job. So the way this is working is we're building up our T one edge at a time. And as we're going along, we're proving what we need to for just the vertices in C. So by the time the process is finished and C is everything, we'll have proved our lemma. Okay, so that's just a restatement of what I wrote down before. We're going to show by induction on the cardinality of C that TC is a tree, and that for each vertex U in TC, in other words, each U in C, we have that D of U is L of PU. Okay, so the base case is pretty straightforward. The very starting case is where the vertex set of TC is X. It has just a single vertex in it, no edges. It's definitely a tree, and D of that vertex X is the correct value. It's 0, which is L of PX. Okay, so now we're going to do the induction step. Okay, so suppose we've got to this stage here. We're now going to add in one more element to C. We're going to finalize the D value of one more vertex. So the next vertex we're going to finalize is this vertex U. It's the one for which D is minimal in U. And when we do that, we delete U from our set U of vertices for which the D value is uncertain. And thereby we add it to C. And we add an edge U which joins U to its parent, which lies inside C. So in other words, we know by induction that the inductive hypothesis is that what we've created in green so far, TC, is a tree. And what we're doing is we're adding a leaf to that tree. And so it stays a tree. Okay, so that's one part of the thing that we have to show, that each time we add an edge to TC, it stays a tree. We also need to check that when we add in this vertex U, D of U is L of P of U. Okay, so what is D of U? Well, D of U, remember, it's been going down, and the very last time it went down, we set it equal to D of V plus L of VU for some vertex V, which by definition is the parent. So D of U is equal to D of V plus L of VU for V, the parent of U. V lies inside C, and so by the inductive hypothesis, D of V is equal to the length of the unique path in the tree joining V to X, i.e. P of V. So D of V is L of PV. But L of PV plus L of VU is the length of PU, because the unique path in the tree joining U to X, or U's at a leaf of the tree, so it travels along UV and then it does what PV did. And so I've shown what I needed to show, namely that for this new vertex, D of U is equal to L of PU. And so I'm done by induction. Okay, so where have we got to? Well, we've been building this tree, T, and we now know that T is a tree. And we also know that for every vertex, its D value is equal to the length in the tree from that vertex to X. But what we need to show is that actually the D value is equal to the shortest possible route in the whole graph from that vertex to x. In other words, we've got to show that there is no quicker way of getting from that vertex to x other than going via the tree t. So in other words, what we've got to show, and this will complete the proof that the algorithm works, we've got to show that t is an L shortest paths tree rooted at x. Okay, so we've defined d of u. I'm going to define d star of u as follows. So for each vertex u in VG, d star of u is L of p star of u for some L shortest xu path p star u. Okay, so it makes sense to consider this quantity. We've got our quantity d of u, and we want to prove that it's equal to the length of the shortest path from u to x. So we've defined this d star of u to be the actual length of the shortest path from u to x. So we want to show that d of u is d star of u. So we're going to show by induction at each step of the algorithm that when u is deleted, we have d of u is equal to d star of u. And so we'll be done. Okay, so the base case is, so we're inducting obviously on the cardinality of C, say. So the base case is when we have just a single vertex, namely when u is x. Well, d of u is the final value of d of u when we delete it from u, for u equals x, is 0. And that's the correct value, namely the length of the shortest path from x to x has length 0. Okay, so that's the base case. What about the inductive step? Okay, so what we're trying to show is that d of u is d star of u for every vertex u. We're doing that one vertex at a time. We're doing it considering the vertex where we delete u from our set u. In other words, when we finalize the value of d. Well, clearly, d star of u is less than or equal to d of u. Why is that? D star of u is the length of the shortest path from u to x. And we've shown that d of u is the length of the shortest path from u to x in the tree. So therefore d star of u is definitely less than or equal to d of u. So the only way they could fail to be equal is if the inequality was strict. So suppose, for a contradiction, that d of u is strictly greater than d star of u. Okay, as usual, let C be Vg minus u. These are the vertices that we have finalized. And we know that, so we're proving that as we finalize each vertex, d of that vertex is d star of that vertex. So for the vertices that we finalized, in other words, for every vertex v in our tree Tc, we know that d star of v is d of v. Okay, so the setup is something a bit like this. This is some graph. This is my base vertex, x. And say u, so these vertices in green, they're the vertices in C. They're the ones whose d value has been finalized. And also in green is the tree Tc. And what we're doing now is we've finalized some new vertex u. So u is the vertex whose d value we're now just finalizing. So this is the stage we're at in the algorithm. And what we want to do is we want to show that d of u is equal to d star of u. And we're assuming for a contradiction that d of u is strictly greater than d star of u. Okay, so we have p star of u. This is the length of the shortest path in the graph from x to u. So it clearly starts at x, which is in C, and it ends in our set U. And so there is some first point when it leaves C. So let y primed be the first edge of this shortest path p star u, with y not in u, in other words y in C, but y primed in u. So this is our first time this p star u leaves the tree. It could actually happen that it ends at u. That's completely fine, but it might not. Okay, so we're going to focus on this edge y primed. Now, by induction, we know that for all of the vertices in this tree TC, they have the correct d value, namely d of y is equal to d star of y, in particular for this vertex y. Okay, so now we have a sequence of inequalities. Some of them are more obvious than others. The first one is possibly the least obvious. I claim that d of y primed is less than or equal to d of y plus L y primed. Okay, so the first inequality is because of the update rule. So what it does is each time we put a vertex into C, we finalize it. What we do is we look at all of its neighbors in U and we say, is their d value greater than d of this vertex y plus the length of the edge? So when we finalized the d value of y, we would have done this for this edge here. So we would have looked at the d value for y primed and we would have said, is it strictly greater than the d value of y plus L of y primed? And if it was, we would have decreased the d value of y prime down to that value. Well, maybe at later steps in the algorithm, the d value of y prime went down even further. But that's fine. We get the inequality that d of y primed is less than or equal to d of y plus L y primed. Okay, next bit is fairly obvious. We've already shown that because of the induction hypothesis, d of y is equal to d star of y, so these two are equal. And by definition, d star of y is L of p star y, the shortest possible path from y to x. And I claim that L of p star y plus L y primed is less than or equal to L of p star u. So why is that? Okay, so p star u is a shortest path between x and u. So that means that any subpath of it also has to be a shortest path joining two vertices, the two ends of that path. Otherwise there would be a way of shortening p star u. So that means that the shortest way of getting from y to x is to go via p star u. So that means that L of P star Y, that shortest way, plus the length of y primed, well, that's the total length of this subpath from x to y primed. That's a subset of the entire of P star U, and so we get the inequality that L of P star Y plus Ly y primed is less than or equal to L of P star U. Okay, so L of P star U is by definition a D star of U. That's how D star is defined. It's the shortest possible length of the shortest possible path from U to X, and we're assuming that P star U is such a path. And remember, we were supposing for a contradiction that D star U was strictly less than D of U. So, putting all these together, we get that the D value of Y primed is strictly less than the D value of U. And that is a contradiction. So why? Well, if you remember, the way the algorithm works is it chooses to finalize the D value of a vertex in our set U with smallest possible D. And we're supposing that it's finalizing this vertex U. But it shouldn't have done, because the D value of Y primed is strictly less than it. That's what we've just proved. And so, in other words, it should have, instead of finalizing the D value of U, it should have finalized the D value of Y primed or some other vertex with even smaller D value that is in U. So that's a contradiction that contradicts our choice of U. And so what hypothesis does that contradict then? So that contradicts the hypothesis that D star of U was strictly less than D of U. So we deduce that D of U is actually equal to D star of U, and that is what we needed to prove. So that completes the proof of the theorem that T is an L shortest path tree rooted at X. And therefore that completes the proof that Dijkstra's algorithm works. So I think it's quite a remarkable algorithm because it's extremely efficient. Let's just analyze its running time. So the running time of this algorithm is big O of the number of vertices of the graph times the number of edges in the graph. So let's just understand why that is. Well, at each stage, what we're doing is we are finalizing the D value of a vertex. So we're running through each of the vertices one by one. So the number of steps is we do that is the number of vertices. But what do we do at each stage? Well, for that given vertex, we look at all of its neighbors, and we possibly reduce their D values. Well, how many neighbors does that vertex have? Well, certainly at most the number of edges in the graph. So the number of D values that it needs to change at any given stage is at most the number of edges in the graph, and so the total running time is equal to at most the number of vertices times the number of edges. In fact, actually, you can slightly rearrange Dijkstra's algorithm somewhat using a slightly better implementation, which we omit, which gives a better running time, which is where which is big O of the number of edges plus the number of vertices times log of the number of vertices. But in any case, the version of the algorithm that I described here really is very efficient. It's bounded above by a polynomial in the number of vertices and the number of edges. And that is what we're taking as our working definition of efficient. In particular, it's much, much more efficient than the naive algorithm of just looking at all possible paths between our pair of vertices, looking at the length of each and just taking the minimum of that. That takes far, far too long. Okay, so that completes this lecture.